folks want to look at it. It's going to be pretty simplistic for what we're looking at, but it's going to drive the point home. So the whole purpose of the talk today is really to look at this idea of algorithms and algorithm analysis, and why that is so important in our field, in software engineering and software development. And too often it gets overlooked, and a number of times, folks will say, well, I found a solution to this. I've got this to work. Okay, that's good, but is it the best solution? In other words, did you create something that's incredibly inefficient and is very, very, very slow, and because of that, it's going to cause some issues. So what I want to do is sort of look at the other side of the coin. If you think of software development truly as two-sided, one being the syntax and the code that you're writing. The other is the actual algorithms by which you're choosing to implement. And sometimes that's the side that gets sort of hand-waved, because it gets real mathy. And depending on folks' background and whether they want to dive in, and we'll get a little mathy today as well as we go through this. So anyway, so let's start with a really simple little problem. Let's start with I'm thinking about a number between 1 and 100, and I want you to figure out what it is. And we don't have to play the whole game, but we'll just talk through how you would play it. And when you tell me a number, I'll tell you whether it's higher or lower. If you played that with a 4-year-old, what would the guesses be? Let me just guess. What's that? Yeah, if you played that game, say, I'm thinking of a number between, okay, for them, I'm thinking a number between 1 and 20, right? Forget the 100, right? 3 digits. But, right, what would their guesses be, right? Maybe their first guess would be like 37. Nope. 12. No, it's higher than that, 72. I mean, it would be all over the place. And eventually, they would probably get the number. But not quickly, right? But that is an algorithm, right? Now, if we were to play that in here, your first number would be what?
50.
50. And I immediately say, well, that's too high. Your next guess is 25. And everybody in here will get it within 7 guesses, right? It would happen every single time, because you've chosen a different algorithm to be a little bit more efficient. Right? Well, this is a great problem to just sort of think about the difference between something that's efficient and something that's not efficient. All of us at some point, whether it's a simple mobile app, whether it's software, whether it's a web page, at some point you're sitting and waiting for something, and it's really irritating. And a lot of times it's not the network. A lot of times it's because whoever wrote it in a very inefficient manner, and it's having to do a lot of work. So that's really sort of the focus today, is at the end, is really, is to get us to a point where we're thinking about how we code things. Not what the code is, but how it actually executes. So let's look at this sketch. So the 4-year-old sort of check every number algorithm. Worst case, it's going to take them 100. Actually, worst case, it's more than that, because they'll repeat and don't realize they've repeated, right? So that's sort of the 4-year-old and 90-year-old algorithm. Okay. Best case, right, if they get it the first time, boom. But on average, roughly probably around 50 guesses or so would take them. The one we just talked about, where you check a midpoint, and if that's not correct, then you choose the midpoint high or the midpoint low, if you're getting the second half. Worst case, it's going to take you 7 guesses, because you're taking the data and you're cutting it in half each and every time. So really what we're looking for is 2 raised to what power is at least 100. In this case, 2 to the 7th is 128. I could play this guessing game with you and just say 1 to 100. I could say I have a number between 1 and 128, and you'd still get it in 7 guesses. As soon as I went to 129, you're no longer guaranteed to get it in 7. It could actually be 8 at some point. And so all of a sudden, you have this algorithm that takes the data and with each guess reduces it by 50% or a factor of 2. Best case, probably about 1. On average, it's going to probably be somewhere between 6 and 7. So quite a few of those. So let's get a little mathy for a moment. I don't know if you remember logarithms much. Boy, no one just jumped up and went, yay! Let's just quickly do a little bit of math review. It's been a while probably for some. But if you have a simple equation, log base x of y equals n, that equation actually means you're looking for x raised to the nth power equals y. So this is it. You have logarithmic and exponential, and they're inverses of each other. The reason this is really important to us is that we look at algorithms, and some of them have what we call log-based analysis to them. The guessing game we just did is a log base 2 with regards to its analysis. So in mathematics, when we write log n without the base, it actually means a base 10 because we work in a base 10 system. Our number system's base 10. But in computer science or software engineering and programming, we're always typically working in a base 2 system, right? Binary. So when we write log n, it really means log base 2n. Now for the purpose of this presentation, I will always give you the base, just so that you know. And again, is this critical to you? Maybe, maybe not. But more importantly, the idea is a log-based algorithm is when you take the data and you cut it in half, and you cut it in half, and you cut it in half. That's a log-based algorithm. So in the guessing game that we just looked at, that log base 2 of 100 numbers says equals x. That's the maximum number of guesses that we would have to find. And so we want to find x. When 2 to the x is greater than or equal to 100, we found it. It was 7. So in that guessing game, we know that it's going to be 7 guesses maximum. Does that make sense? I don't know if you remember logarithms or not, but just understanding what it means, we're really talking about an exponent here. When we look at algorithms, if we've developed some sort of an algorithm that for a given data set of size n, that we do some operation and it reduces that data set in half, and we do the same operation and it reduces it in half, that algorithm, the analysis for that algorithm is going to be considered to be a log-based algorithm. Okay, that's really what we're talking about here. Now, let me throw out another idea to you. Okay, let's do a little scenario here. Let's assume for a moment that you own a pet moving company. Sounds really cheesy, right? And I come to you and I say, I have 2 pets that I need moved. I'm moving across state, and you guys move pets. I have 2 pets, all right? And you're like, no problem. What are they? I have a goldfish and I have an elephant. At this moment, in your mind, I don't have 2 pets. I really have 1. Goldfish, piece of cake. Put it in a jar, we're there. The elephant's going to be a problem, right? In other words, in that scenario, one of those is really consuming all of the energy and resources. The other one's just trivial. So I could have come in and said, I have an elephant. You would probably charge me about the same as if I have an elephant and a goldfish. Does that make sense? It's a cheesy example, but it has everything to do with algorithms, right? So there's this thing that we call big O notation or big O comparison when we do algorithms. And what it refers to is the type of algorithm. This is really sort of tough to see. Let me hit full screen here on this thing. Let's see if that helps it a bit. Helps it a bit. So what we have are, these are considered to be complexities. So think of it this way. If you're writing a piece of software and the amount of data that you're working with is along the x-axis, then the y-axis represents the number of operations or the number of calculations that have to be done, which really means the efficiency or the speed. The higher up you are, the slower you are because you're doing more calculations. Does that make sense? So obviously if we have a piece of software that only does 10 calculations versus a piece of software that does 1,000,000 calculations, the one that does 10 will be done far faster. Okay? So these graphs here represent different categories of algorithms. And you can take a problem and solve it using any one of these categories of algorithms. Well, if your solutions tend to be in this blue or orange, which happens to be either 2 to the n or n factorial. I don't know if you guys remember factorial. That's important today too. Just real quickly. Sorry, we're getting mathy on you today, right? So factorial, like 4 factorial, is 4 times 3 times 2 times 1, right? Which is 24, okay? Just remember what the operation is. So if I say factorial, that's what we're talking about. So if I had an algorithm that had 4 pieces of data and it was coded in a factorial-based algorithm, I'd have to do 24 operations in order to work on those 4 pieces of data. That's really what we're talking about. So here you can see that, say the green line, which is n. So if I have 10 pieces of information, I have to do 10 operations. If I have 60, I have to do 60. If I have 100 pieces of data, I have to do 100 operations. That's actually pretty efficient. The purple line is actually n log n, which is a really common algorithm. A log-based algorithm, like what we just talked about, we had 100 numbers. And we knew maximum number of guesses was 7. If I play that same game, and I'm thinking of a number between 1 and 1,000,000, and we played that game, anybody have any idea how many guesses you have to make? 20. You'll get it in 20 guesses. That is incredibly efficient. Think of the 4-year-old scenario. I'm done playing now. Right? 1 to 1,000,000,000. 1,000,000,000. If I have that many pieces of data, if I have just a log n, not n log n, but just a log n, which is by the way, that's the red one down here. You see how it's almost flatline? If I have 1,000,000,000 and we're playing that game, 1 to 1,000,000,000, anybody know how many guesses? 30.
20 to the 10.
What's that?
2 to the 20 to the 10.
No, 2 to the 20th or 2 to the 30th.
Oh, yeah, but I figured it out. 2 to the 20th was 1,000,000, put it around parentheses, and 2 to the 10, and then you add the exponent.
Right, and then you add exponents to go that direction, yes. So we're talking about 30. 1,000,000,000 numbers. I'm thinking of a number between 1 and 1,000,000,000. Go. And you would get it in 30 guesses. Man, that is instantaneous, right? So that's really, really, really awesome. If we can ever get an algorithm that's log n, that is the golden standard. If we can do that, it's incredibly fast. Now, it's common to get what's called n log n, which is an algorithm that has some logarithmic to it, but then it's multiplied by the number of elements that you're doing. And then they start getting really bad. Right. This sort of, whatever color that is, I want to say cyan, I don't know. Anyway, this bluish one, this is called an n-squared algorithm. So if I have 100 elements, I'm now doing, what do I got, 10,000? Right, 100, 4 zeros, right, 100 times 100, I'd have to do 1,000, or 10,000. If I have, it's squared, and it goes up very, very, very quickly. The orange one here, this is 2 to the n, right, 2 to the n, which is huge numbers. So, which we'll look at in just a moment, because it's sort of fun to see exactly how big that number is. It's massive. And then this one here, this one is, actually the blue one is, oh, that's n factorial. Yeah, I can't even calculate that one because we don't have enough time in our lifetime to do that. So as an example, just to give you a feel of how long these are going to take, I do have, we're going to go over here and we're just going to use some Python real quick. Python's an awesome little language. So I'm just going to go into the Python interpreter for a second. So let's say that we're dealing with something that is that has 1,000,000 elements. Let's do that. That's always fun. So if it has 1,000,000 elements, log-based of 2 of 1,000,000 we said was 20 roughly. It's like 19 point and some fractions. So we'll round it to 20. So we know if we can code it that way, we only have to have 20 operations. If we have 1,000,000, let's say we do n log n, right? Well, then it'd be 20 times 1,000,000, so that'd be 20 million. That's okay. It's still actually pretty good. If we did n squared, right? You got 1,000,000, 1, 2, 3, 1, 2, 3 times 1, 2, 3, 1, 2, 3, right? So we're up to whopping 12 zeros. We're getting a little bad on that one. The next algorithm, that was at n squared. If we go to 2 to the n, sorry, I'm jumping around. Where's my shell? What's 2 to the million? Okay, it's this number. And this number, if I were to, stop. Come on, let me in here. There we go. Okay. So it scrolls for a while. It's going to scroll for a long, long time. You see my scroll bar in the right corner? Okay, I'm going to stop. Just for fun, I mean, I could take what I have just to get an idea, and I go into Word. I have nowhere near do I have that. Actually, you know what? Let's do a number that's not so large. How about 2 to the 100,000? That's far better. So that's that number, which is still huge. Anyway, so these are big numbers, right? Think if your computer had to do, oh, there it is. Back up. Oh. Oh.
Control A. Control A and then delete.
Well, Evan, I got a ton of stuff up top. That's okay. I'm just going to grab it and go. As soon as we see that little space, which won't take long, everybody's watching. It's going to be there. It's going to be there. Oh, there it is. All right, so I'm going to go there. I'm going to copy it. Let's go into Word. Okay, I cannot see underneath this thing. There it is. Go into Word. I'm going to paste it and then do a word count. It tells me how many characters it is, right? Come on. Where's Word? It's there. Oh, it's because I have this thing. Can I move that? I can. That's nice. All right. So I'm going to paste this, and then I do a tools, word count. So that's about 30,000 digits. And that was just 2 to the, what did we do, 100,000? Okay, so 2 to the million is massive, right? So, and that's if you had a data set of 1 million items. This would take forever. Would take.
You're saying 30,000 operations.
No, I'm saying there's 30,000 digits in this number that represents how many operations has to be done. Which is big. Really, 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 really big. Okay, so we can see real quickly that, okay, now I got to get everything responding back. All right, there we go. So when you do an algorithm, this is good, this is bad. Right? We want to be able to have our algorithm scale as we get more and more and more data. We don't want our software just tanking, right? We don't want it to just completely stop. We want our algorithms to be as efficient as possible. And sometimes n squared is as efficient as possible. It's really icky, but sometimes that's as good as it gets, right? So anyway, let's look at some problems. Now we'll do some problems, and then we'll actually do some a little bit of code running. So let's start with this one. I have 8 identical looking coins, but one of them is fake. And I want to know what is the fake one is slightly less, it weighs slightly less. What is the minimum number of weighings that I must make in order to guarantee that I found the coin? Okay, so you have 8 coins that look identical. All right. Now let's start with, let me ask you this question. What is an O sub n, or in other words, what is an n-based algorithmic solution for this problem? So I have 8 coins. Is there a way I can solve this by making roughly 8 weighings? Okay, can you come up with a solution that does that?
You can do it in less than 8.
Of course you can.
But you said minimum number up there.
Right, and we're going to get to the absolute minimum.
Okay.
But what I'm trying to do is show you that you can have solutions at different complexities, at different efficiencies. So let's start with just an n solution, right? I could just take the coins, I could take 2, I could weigh them. They weigh the same. I'll put one away. I'll get the next one, I weigh it. That weighs the same. I'll get the next one and weigh it. And when I'm done, I will, if the last coin happens to be the fake one, I will have done 7 weighings, right? Because I will have started with the 2, then 3, 4, 5, 6, 7. I will have gotten through all 8 coins. So that is an n solution, what we call a big O, or a big O analysis of n. If I have n coins, it's going to take me roughly n weighings. Is it a solution? Yes. Not the best, but it is a solution, right? So if I had 1 million coins, I could come up with the fake coin by weighing roughly 999,999 of them, if the last coin was the fake one, right? I could go through and do that. Okay, can you come up with a log-based solution? Now, a log-based solution, what do you do? Think of the data set. Remember the guessing game? What did we do with our data? We cut it in half, and then we cut it in half, and then we cut it in half. Can we do that with this? You take 8 coins, what do?
Split.
Put 4 on one side, 4 on the other. Now what do?
Take the lighter one.
Take these, 2 and 2. Right? Take those. So I can do a log-based solution, and I can do 3 weighings. Everybody see that? Now, how do I know? I'm sorry, I know you're doing camera. I don't know if you see this over here. But how do I know that 3 would have been the answer to this? If I was doing log. If I'm doing log, if you remember, logarithms are exponents. I'm really looking for 2 to the what is greater than or equal to 8. Give me the smallest number that's going to be an exponent that makes that true. 3. 2 cubed is 8. So I know I should be able to solve this in 3 comparisons. That's a log-based algorithm. Anybody come up with something less than 3? I can do it in 2. Now I got you thinking. This has nothing to do with n or n squareds or anything like that. Just this particular problem. We'll come back. We'll come back to it. Let you think about it a bit. How would this change if I said I have 9 coins?
Plus 1
Plus 1
to that one.
to that one. So I could look at if I did this, what this number has to be what now? Has to be 4, right? So if I do a log-based 2 algorithm, I have to make 4 checks. Which means somehow I have to be able to split my data in half. What if I split my data in thirds? Can I take my data and split it into thirds? Yeah. I leave 3 coins off the scale. My apologies. I leave 3 coins off the scale. I put 3 on one side, 3 on the other. If they balance, the fake is in the 3 coins. What do I do with those 3 coins? 1, 1, and leave 1 out. If they balance, it's the one I left out. If they don't balance, it's the lighter. If the original 3 and 3 didn't balance, I do the exact same thing with those 3. So that actually there becomes a log-based 3 algorithm. Sort of an interesting. Right? So this is actually, we just did it. I forgot about that slide. Let's go back here. Now that you just saw that other problem, that introduced a type of solution that we didn't consider in this first one. Leaving coins off the scale. You guys went 4 and 4. Do I have to go 4 and 4?
4 sets of 2.
What's that?
4 sets of 2.
Okay, if I did 4 sets of 2, then if, let's assume they don't balance, right, then I got it.
Yeah.
If they do balance, off, got to put these up. My second weighing will tell me which pair has the fake coin, and then I weigh it again, but that's 3. How can I get it down to just 2?
3, 3, and 2.
Perfect. What do you leave off the scale? The 2,
The
right?
twos.
I go 3 and 3. If they balance, I weigh these 2. If they don't balance, I have an odd number. Leave one of them off and weigh 1 and 1. Nice. Very good. Now, these are really sort of simple little problems, but they get you thinking about efficiencies. Right? That's what I'm really trying to focus today on, is when you code, you have to think about efficiencies. What's the best way to do this versus just any way? No pun intended. Ba-dum-bum. Okay, pun intended. All right. So let's look at another problem. This one's fun because this is where we're going to have some fun with this one. We'll run some code. My grandfather, rest his soul, he was a game player, and not like millennial game player. We write board games, anagrams, crossword puzzles all the time. He loved anagrams, and I grew up as a little boy always playing anagrams with him. And so I have so many examples using games that I've done with him. But an anagram, we're talking about two words that have the exact same letters. Or it doesn't even have to be a word, it could be a whole sentence, right? Or paragraph, whatever. Does it have the exact same character composition as whatever you're comparing it to? All right? So like Python and Typhon, right? Those are anagrams of each other. Now, without me biasing you, how would you solve the problem? What would you do? How could you solve that problem? And don't think of code. Don't worry about coding. Just talk through it. How would you solve that problem? Anybody want to offer any solution? Doesn't have to be great.
I just start with the first letter of the first word and see if it's in the second word, and the second letter from the first word, see if it's in
Good. And that's
how
an
I do it.
That's an n squared algorithm. Because what you have is you have a nested for loop. For those who are actually coding, you have a nested for loop. For each letter in the first word, you go inside. For each letter in the second word, compare. So that means you're going to compare the P, the initial P to the T, and the P to the Y, and the P to the P, and the P to the H, and blah, blah, right? And then you move on to the Y. Compare the Y across, et cetera, et cetera. Okay, excellent. That's an n squared algorithm. That is a solution. That's this line. Okay? Are there other solutions? Are there solutions down here for that same problem?
Just number of letters. I mean, you know right away if it's
Okay, if they're not the same length, you know right away. But if they are the same length, are they anagrams?
that's the same question.
That is the second question,
You
isn't it?
stop searching the second word once you find a match, instead of going through the whole.
Sure, and you would,
same
and
sum.
you would in that case, because otherwise duplication, letters that are duplicated would really cause you some problems. But that still ends up being an n squared algorithm. And we're back to the elephant goldfish. I was just about to go for it. Whoa, okay. I felt like I was in my lab. These are my whiteboards, and I'm going. Okay, that's not a good thing. So if we have an algorithm, let's say that, like you just talked about, where probably the easiest thing is if I did, let me just draw a little picture. Really what we're talking about is doing that, and doing that. You guys get this really ugly picture? Okay. And so n represents how many letters in our word, okay? So if we have 5 letters in each word, and we do an n squared, if we don't stop early, we have 25 comparisons. Everybody see that? 5 letters times 5 letters. Okay. For those that are, if you're struggling with this concept of nested looping, another really easy scenario to think about. I use this in my class all the time because I have like 18-year-olds and it makes total sense. If we take all the guys in this room and we take all the girls in this room and we want to know what are all the date combinations for Saturday's dance, right? It's a nested for loop. For each guy, for each girl, match, right? Bob to Sue, Bob to Sally, Bob to Pam, John to Sue, John to Sally, John to Pam, right? And away we go. And they're like, oh, I get it now. Okay. So anyway, so we got 25. Now if we stop early, if I only have 25 and I stopped a few times through there early enough that maybe it took off 7 comparisons. I'm just sort of randomly picking a number. 7 out of that 25, that's pretty good. I mean, that actually probably helps us. What if we have 1 million letters and we're able to cut off 10,000? Doesn't really matter. Do you see what I mean? The larger you scale, it's back to the old elephant goldfish. How much for my elephant? $1,000. Okay. I also have a goldfish, but I don't know. It doesn't matter. Right? We'll throw the goldfish in for free because it doesn't matter. And the same thing is true here. So mathematically, sorry to get mathy on you again. So mathematically, when you do algorithm analysis, you actually create mathematical functions that represent it. So let's say I did an analysis and our particular elephant goldfish thing ended up being something like, x squared plus 3x plus 7. Let's say when we were done with our analysis, we'd end up with that. Well, if I have 2 pieces of data, 2 squared is 4, 2 times 3 is 6, so that's 10 plus 7 is 17. That 7, boy, that really changed it from 10 to 17. That's a huge change percentage-wise, isn't it? That's a 70% change. What if I have 1 million? What does that 7 do? Not a thing. It's a mosquito bite, right? Because we're talking about 1 million squared plus 7. Oh my gosh, I'm so sorry. 1 million squared. Did you guys even hear that? Okay. I wasn't sure. I have hearing aids that are Bluetooth, so it rings in my ears before it hits you guys. So I try to get them cut off real quick. It's cool. It's totally awesome.
The ring was self-evident, so.
Okay, I wasn't sure whether you were getting a ring or not getting a ring. I will try to turn the ringer off. Yeah, that one's not my ears.
Did you hear that?
Yeah. So anyway, the point is as you're doing this algorithm analysis of and you're analyzing code and how what are the processes or the comparisons that have to be made, what are the operations that are going to get done, you end up with sometimes mathematical like polynomials like this, and at the end of the day, if we're dealing with a huge amount of data, that 7 completely irrelevant. This is why I love computer science, because we just throw it away because it doesn't matter. I love being able to do that. And if we're dealing with 1 million, what about 3x? How big does that impact it?
3 million.
3 million. But 1 million squared? Yeah, whatever. Right? This was the elephant. The other was a cat and a goldfish. Do you see what I'm saying as far as the size? So as things get huge, you're really only concerned with the big inefficiencies. Okay, so we'll go to we'll go back here. So one way would be to do n squared, and I've actually coded up using Python, and I'll share the code for those who want it. You can email me at the end, or I'll just send it to you if you're interested in it. 4 solutions. One is an n squared solution, because that's the most common. And so I want to take a look at that. So let's go and let's actually, so here's my next slide. I thought it was funny. Okay. It's funny to me.
Oh, demo disgusting.
Demo discuss. That's what we're going to do. All right, so where is my shell? Oh, here it is, yes. All right, so let's get out of this for a second. And I need, this is actually written in Python 3. All right, so I wrote, what's that? Oh, you don't see it. Why don't you see it?
You're in slide.
Oh, thank you. Thank you very much. You are correct. I need to get out of that. End show. Okay, kill. No. There we go. Clear. All right, so now I wrote this little Python program where we can enter stuff in on the keyboard or we could read in from a file. So let's do this. I want to enter from standard in. Yes, I do. Okay, so let's do some words. Let's do like if I did. They don't even have to be words. Q A Z W S X. So I'm just doing a diagonal on my keyboard so I can remember what it was. So that's my first word. And if I do the same diagonal but maybe go backwards, W S X Q A Z. Those are anagrams. Everybody sees that, right? The exact same? Okay. So now I have 4 solutions coded. I also have it timing. It will tell us exactly how many milliseconds or seconds that it takes to solve this problem. So let's choose solution number 1. Okay, so it is an anagram and it took us, what is that, tenths, hundredths, thousandths? So 10/1000th of a second to solve that problem using that algorithm. Pretty good. Didn't have to wait. I'm not done. Solution 2. Okay, that took, boy, that's even faster, huh? Tenths, hundredths, thousandths, 10,000ths, hundredths. That's 6 100ths of a 100,000ths of a second. There's a lot of THs in there. So that looks pretty good. Am I done? No. Let's do third one. Okay, that looks like somewhere in between. And am I done? No. We'll do number 4. Yeah, that didn't look so good. I mean, it's still incredibly fast. So if our job was to write an app that people could plug in 6-letter words, and it would tell us whether it's an anagram, you probably could choose any one of those 4 solutions and it would work just fine. Because 3, I always have to go through it, tenths, hundredths, thousands, 337 10,000ths or whatever, compared to this one up here, right? Those are instantaneous for the human. It's not a big deal. So this is what happens with a lot of people when they learn to code. As they learn the syntax, they create a solution, and it works in the small. What happens when it scales, right? And we say, are you done? Yes, I am. So let's do it again. Actually, I should put it up top again. It's easy to see that way. You guys are able to see that? Yes? Do I need to make it larger? You guys okay? Okay. We'll do standard in. So this time, let's go 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just going down my diagonals. So there's 9 letters. All right. That one seems to be screaming fast. That's good. You know it would be probably even good to have on the screen as we do this. How about we do that so you have something over there to be looking at comparison-wise algorithm. So that one was smoking. Am I done? Yeah, no, is the correct answer. 2. Okay, that was better. Am I done? No. 3. Boy, 3 looks like that thing's maybe slowing us down a bit. 4. Okay, that one was substantially less efficient, it appeared. Okay.
Is your 4th solution the n squared?
Well, that's what we're going to find out, aren't we? We're going to find that out. So let's say I am done. Let's try it again. We'll do it one more time from the keyboard, and then I have some files that we could load. So let's do this one more time. And standard in, yes. Let's do 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My first word. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's my second word. All right. That thing doesn't seem to be moving, right? Am I done? No. Number 2. That thing seems to be even doing better. That's nice. No, I'm not done. 3. Again, these things don't seem to be really doing much. So let's talk for a while. Every single one of these is a valid solution. And you saw a moment ago, they solved the problem. Every one of them solved the problem. And it did it pretty quickly. And now all of a sudden, I have one solution that I just went from 9 letters to 12 letters. And we're going to sit here for a couple minutes. Okay? So just from what you've seen, what might you guess? I will tell you this. There are 4 separate solutions over there that I've coded up. I've actually done 4 of those 1, 2, 3, 4, 5, 6 lines. All right? By the way, on all future demos today, we will not choose number 4 because none of you have enough time for it to finish. In fact, some of the examples we'll give probably won't finish this year, and some actually probably wouldn't finish before I die. All right? Which, by the way, is supposed to be a long time from now. Just
for the record.
For the record, I want to make sure we're all clear on that. You're like, is there something planned? No, nothing planned. So, just from this, anybody want to take a shot at what you think number 4 is? And it's not the n squared. One of the other 3 is the n squared. And that's the n squared is this line. Right? This is n squared. So I've obviously done one of these 2. And I've actually done the worst possible. I've actually done the factorial. Okay. So, so this is horrible, and it should be done in a minute. There we go. So 131, almost 134 seconds to complete. All right, and that was just going from 9 letters to 12 letters. All right, that's a pretty significant. You think that's should be pretty easy, but you would never know it if you coded this up and you happened to choose the 4th solution, and you tested it on a 4 letters, 5 letters, 6 letters, 7, 8, 9. Yeah, it seems to work pretty good. And you don't scale up, you'd never see it. Okay. Am I done? Yes. All right. So one of the things that I have here is I also grabbed. Abstract.txt. So I also grabbed off of our meetup the abstract for this talk. This was the abstract on what do you guys use?
Meetup.com.
Meetup.com. So I just grabbed that abstract, threw it into a file. So that has more than 12 letters. We're not going to do that on number 4. But let's go ahead and play with this. Let's see what that does. That's going to be a pretty substantial increase in size. So if I come along and say, okay, well, let's do enter data via standard in. No, I want to do a file. We're going to do abstract.txt. Thank you. Fat fingered it. Abstract.txt as 1. Abstract2.txt is the other. Okay, so first solution. That's pretty good. Because that's quite a few letters. Am I done? No. Boy, that looks really nice. Doesn't it? No. 3. That one looks pretty good. Those are almost identical. We're not doing 4. All right? So, okay. So now you're like, well, I think this thing will scale pretty good because that was a pretty sizable amount of text. I think this will work really, really well. So what is this? How about the entire Dr. Seuss Cat in a Hat? Or Green Eggs and Ham, sorry. We'll do Green Eggs and Ham. So, come up, which is far more characters than the abstract. Nope. Not standard in. Green eggs.txt and green eggs 2.txt. And what I did in these files is I took the entire thing and then I took like 6 lines and I just moved them to the bottom. So they are truly anagrams, but you can't just compare them one letter, right? You can't just take them and compare the first letter, second letter, third letter, fourth letter. You can't do that because they're not in the same order. So we'll go through and say, okay, what about green eggs and ham? Okay, took a little over a second. Still not bad. Although a second is just about maximum time that a user will wait before clicking something. If it pauses, they're going to, they hit another couple times. Now you got inputs queuing up, right? So you have to realize that. Am I done? No. Let's go for solution 2. Okay, now these are starting to spread out now. Now we're starting to get enough data that you're starting to see a difference in these. Looks like that second and third are still pretty close to each other. That first one is starting to spread out. But still not bad, right? That's pretty long. Again, we will never choose number 4 again. We will never choose number 4 again. I'll just choose number 2 again because it'll go quick. There we go. Am I done? Yes. And how about the following? No. This is the entire works of William Shakespeare. Okay? In a single text file. It's pretty long. Okay? And William2.txt. I'm trying to think whether I ran this one at home. I may not have. This could take a while. I don't know that I want to wait. Very impatient. Okay, I'm not going to wait. I'm killing it. We're starting over. Yeah. So we're not going to do number 1. So which one is number 1 up here? The really bad one was here. Number 1 is your n squared. It's using the exact algorithm that you described. Okay. So we'll look at 2 and 3 and see how they do. Standard in, yes, no, do file, and William 2. Okay, number 2. Not bad. Just barely over 2 seconds.
Number 3, 1 second.
Think so? Are you done? No. Number 3. 1.8. All right. That's not bad. The entire works of William Shakespeare. right? That is a very, very, very large file. It's not 12 letters like we did a moment ago, okay? So what are these algorithms, okay? Let me tell you what each one is. I'm going to describe how I solved it. The first one is the n squared. So at small amounts, it worked pretty fast. The second is an n log n algorithm. The third's an n, and the fourth is the n factorial, which is just horrible. So how did I solve these in different ways? This one was exactly what you described. Take the first letter, find it in the other one. As soon as I find it, stop. That's even with the exiting. Okay? Then go to the next letter, and go all the way through. Solution 2 is saying, well, I have these two long files that are the same length. That's key, right? Because if they're not the same length, they can't be anagrams to start with. So they're the same length. What if I sorted them all? What if I took this one and forget? I don't care about the, all the different William Shakespeare quotes. I just sort them, A through Z. I'll probably have pages and pages and pages of A's, right? And then B's and then C's, etc. I do that to both, which, by the way, to sort a file is a n log. It is an n log n algorithm to sort it. That's where the meat of that. Then all I have to do is I compare the first letters of each, the second letters of each, the third letters, and I just compare. If they're ever not equal, what do I know? It's not an anagram, right? So there, the cost, the elephant, is in the sorting of it. To walk the list is just n. So this technically is an n plus n log n, but the n plus, that first n is like the goldfish. Doesn't really matter. The n log n is a big piece. And so that's how I did that one. Here, how do you do it just n? How can I do it just passing through them? Hopefully those, I think most of you know, if you're coders, might be familiar with this. It's called an Ascii chart. Every letter has a particular value. There's 128 characters in Ascii. So I created an array, 128 character array, 0 to 127. Then and I set them all to 0. Then all I did is I just took character after character and said, what is your value? And I add one. So when I get done, that array has how many A's, how many B's, how many C's, how many D's, how many spaces, how many exclamation points, how many parentheses. I just counted letters. And then I do the same thing with both files, and all you have to do is walk through it once. Because then you have the counts, and then I look, are the counts the same? If they're the same, they're anagrams. And that was an N version. So
Why is that not 2n? I mean, you go
technically it's 3N.
Yeah.
Well, actually it's 2N plus 128. But if you're,
okay.
right, because you have N for one file, you have N for the other.
You just lumped it into that category even though it's
Right,
okay.
because again, as it gets infinitely large, N, 2N, it's N. That's that whole hand waving of algorithm analysis that comes into play. So you're right. It's in the category of an N algorithm. So the whole point of sort of this chat today was when you guys are finding solutions, how do I do this? How do I take this data and I got to do all this stuff with it and I got to store it, etc. The data structures that you pick, how you store things, how you solve the problem, whether you're using nested loops, whether you're not using nested loops. This is a nested loop. This uses a single loop. Solve the exact same problem, far more efficient. Those are things I want you guys to think about as you go into the career. It's not just the syntax. Coding is just part of the equation. The algorithms really are what gives you the power and the performance. So anyway, that's what I have to share. What I will do, and I didn't do this earlier, let me throw a quick new slide on right now. I'm going to throw my email on it. So if you want If you want the slides, you're more than welcome to have them. They're not that exciting, but and the code. If you want the code, I'll send you the code as well. All right. So so my email is Brent B Wilson. Jeez Louise Wilson. Come on. B Wilson at georgefox.edu. That's just really cheesy, isn't it? That's funny.
The plug for your.
Yeah, that was marketing. That was all marketing right there. Anyway, you're more than welcome to send me an email, and I'll be glad to send you this if you're interested in it. So anyway, so thank you. I appreciate letting me come in and just sort of chat with you. I hope that made sense. It's all about elephants and goldfish. That's what it's all about. All right, thank you.
I really want to slide this as demo, discuss.
You like that one? Yeah. So what did you go over today? Right here. Demo, discuss. Well, you're welcome. Yeah, a lot of times that algorithm stuff tends to, it's the theoretical, it's the performance, it's the, I tell my students the difference between a beginning programmer and a seasoned programmer